Scientific papers say the glass is scattered over 6,500 square kilometers of desert.
Well, it's not clear to me whether the current distribution was the actual distribution when the event occurred.
The Sahara only started to become a desert about 7,000 years ago. And during the last 30 million years, there have been big rivers and lakes here.
What I think is that the glass was originally at a much smaller area.
It's hard to believe looking around.
And now it's just sand and nothing but sand. There were lakes here some time ago, and there was some water, and it transported the glass farther away from the area where it originated.
Boslow is now confident that 30 million years ago, the distribution of the glass in Egypt was smaller than now, but it still needed a massive event to produce it. He fed the latest data into his computer model.
What we modeled is 120-meter diameter object entering the atmosphere at 20 kilometers per second, and we started off the simulation way above where this frame starts.
To explain the evidence of an actual impact found in the desert, the simulation allows a fragment of the meteorite to reach the ground and make a small crater. But such a small impact would not produce the glass. The simulation also shows something far more powerful is happening at the same time. Before reaching the ground, the incoming meteorite is burning up, leaving a trail of incandescent material in its wake, a massive column of fire which turns into a fireball.
The widest temperature here is the temperature of the surface of the sun, and as it expands, the fireball is actually pinned against the surface, and it's moving very rapidly beyond hurricane force. So we've got this blast of air that's hotter than the melting temperature of the sand, blowing across the sand, so it's melting the top surface, and then that melt freezes to form the glass.
And just like when Shoemaker Levy impacted with Jupiter, an enormous plume of searing gas is streaming out into space.
So while all this material is creating this fireball down on the ground level, there's also a plume that's being formed at much higher altitudes, 80 to 100 kilometers above this level, and it's ejecting material out into space.
The simulation shows that even a relatively small 120-meter meteorite can create a fireball hot enough to produce the mass of glass in the Egyptian desert. It's an explosion that makes the first atomic bomb at Trinity look tiny.
And what I want to emphasize is that it's hugely bigger in energy, hugely more powerful than the atomic test at Trinity, 10,000 times more powerful.
Wasson and Boslow now think they've solved the mystery of how the desert glass was formed in the Great Sand Sea. "30 million years ago, an asteroid was on a collision course with Earth, heading for Egypt. As it began to burn up, it created a hot plume in its wake. Before reaching the ground, it exploded into a blistering fireball. Surface temperatures immediately reached 1,800 degrees Celsius. The ground, which was mostly sandstone, melted and was transformed into yellow-green glass. Above the surface, a column of superheated gas propelled itself into space. The total effect was far more devastating than if it had simply hit the ground. The theory predicts that an aerial explosion is much more likely if an object breaks up easily, like the fragile comet Shoemaker-Levy. So how common are fragile objects in space? An encounter in 1997 proved an eye-opener to the scientific community when a NASA spacecraft flew past an asteroid called Matilda. Matilda's slow rotation showed it was not solid, but was a loose assembly of rock held together by gravity. They call it a flying rubble pile.
We've discovered a number of other asteroids which have similarly low densities, and this has led to a real paradigm shift where now it's accepted that most asteroids probably consist of rubble piles and are extremely weak.
These rubble piles are liable to explode if they enter the Earth's atmosphere. Wasson believes that small explosions, like the one over Tunguska, could happen as often as once every 100 years. Larger ones, like the one over Egypt, are less frequent. Wasson has evidence from one other place on Earth of a large aerial burst, this one on a truly cataclysmic scale. He's found pieces of glass throughout Southeast Asia.
They can be recovered from a broad region of Thailand, Vietnam, southern China, and Cambodia. The curious thing about it is no crater has been found.
Wasson believes that about 800,000 years ago, a flying rubble pile broke up whilst on a collision course with Earth. Each fragment created its own fireball.
Within this region, certainly, all the humans would have been killed. There would not be any hope for anything to survive.
Can we protect ourselves from this happening again? The suggestion in recent Hollywood films that a large asteroid heading for Earth should be blown up is possibly not the best idea.
In those movies, yeah, Hollywood certainly got it wrong. You can't just explode an asteroid just before it hits the Earth and suddenly the pieces disappear. Now you have a lot more smaller pieces hitting the Earth, and they're all making fireballs. You could actually make it much worse by attempting to explode an asteroid just before it collided with the Earth.
Blowing up the asteroid would have the unfortunate effect of greatly increasing the chance that one of the pieces might explode over a built-up area.
While the probability is small, if it hit in the wrong place, it could be devastating for a city.
In a city like London, the devastation from even a small fireball could extend over an area 8 miles across. Luckily, it could be millions of years before we have to deal with a large asteroid. But the smaller ones will keep coming. And we know now from the explosion in the Egyptian desert just how devastating that can be. And we also know it will happen again.
There are hundreds of times more of these smaller asteroids than there are of the big ones that the astronomers track. There will be another impact on the Earth. It's just a matter of when.